Unit Operation Classroom. Today we are discussing packed bed adsorption breakthrough and unused bed capacity. My name is Shikhar Bhattacharjee. A volatile organic compound, VOC, typically these are like solvents. It could be like methyl ethyl ketone, it could be isopropyl alcohol, benzene, xylene, toluene. These are used for various purposes in paint industry, in pharmaceutical industry, in electronic component manufacturing industry. So, but they are very harmful for the environment, so they have to be removed or captured before the air is discharged into the environment. So this is a problem on that. A VOC is to be absorbed. So remember, this is adsorption, not absorption, not absorption. There's a difference between the two. So this is not absorption, this is adsorption from air onto a bed of activated carbon. So let's say this is the system here. So here a gas, maybe air, laden with VOC. So this is like a fan which pushes the VOC and air mixture through this activated carbon bed. So this activated carbon captures this organic carbon. That's the property of activated carbon, and the clean gas, that means which does not have VOC, that just goes out, yeah, and it's discharged to the environment. The equilibrium capacity of the activated carbon at the feed condition is zero point 0.4 grams VOC per gram of activated carbon. So let's say this is my activated carbon bed, and what it is saying that the equilibrium, so at equilibrium, which is the maximum adsorption capacity, that's the maximum this activated carbon can absorb, is zero point 0.4 grams of VOC per gram of the activated carbon. That is the maximum capacity. The column contains 4 grams of activated carbon per centimeter square of the cross section. So, if I take a 1 centimeter square cross section, so this contains 4 grams of activated carbon. Now, how many total square centimeter we don't know, but it could be like 100, it could be 50, it could be 75, 78, whatever. So, why not we take the basis as 1 centimeter square? Okay. So this has 4 grams of activated carbon per square centimeter of the cross section. Okay. All right. The feed rate into the adsorber column is zero point 0.2 grams of VOC per square centimeter per hour. So here in this one, so we don't know what is the total flow. We don't know what is the total flow rate, but we know the flow rate is given as total amount of VOC per centimeter square per hour. So total amount of VOC which is coming in here. So basically, in terms of grams of VOC, let's say benzene or whatever, is coming here per square centimeter. That means divided by this cross section of this one per hour. So that's the unit of this inlet or input flow rate of the VOC into the packed bed adsorber. So, breakthrough time. So, what will happen? Let's quickly understand what happened. So, let's say we have, a packed bed absorber here. So, packed bed absorber. So, when the hydrocarbon enters, so this is let's say air plus VOC. Let me write it down properly here. Let's say this is air plus VOC, which is going in here, which is going in. So as it moves up, this gets absorbed onto the activated carbon, and only clean air comes out from here. Okay, so as more and more air plus VOC comes in, after certain time, what happens? Just a slight amount of VOC shows up. So that's what it is called the breakthrough. And then slowly, as it is get more spent, more and more hydrocarbon gets absorbed, the concentration here keeps on increasing until it almost at the end. That means when its maximum absorption capacity is exhausted, at that time, whatever the concentration is coming in here, C0, the same concentration coming in here. So here, if we take the C as the concentration going out, so at the end, initially here, C by C0 would be is equal to 0 initially, but at a certain point what happens is just shows up, so that at that time C by C0 has a certain value, and at the end, of course, C by C0 becomes equal to C0 by C0. That means there is nothing gets absorbed. It has to be, this is called spent hydrocarbon, and CO0 by C0, that means whatever concentration comes in, same concentration goes out, and therefore this becomes equal to 1. And that's what we are showing here. So basically what happens, the curve, so if we plot C over C0 against time here, so initially it's really goes something like this. There's nothing comes out here, but at a certain point, what is called the breakthrough point, that is TB, just a certain amount of concentration shows up. What is that certain amount of concentration? In this problem, according to this problem, and that is also industry standard, we say C by C0 is when it's equal to 0.05. That means concentration is 0.05%. That means 5% of the inlet concentration. At that point, we call that the breakthrough has been achieved. Not that when the breakthrough has been achieved, the entire carbon has been utilized, but that's just initial point. And then slowly the concentration keeps on coming, increasing up to a point when I said that this concentration becomes equal to C0. That means C0 by this becomes C0 by C0. That means becomes equal to 1. So this is the point. It's called the breakthrough time TB. Okay. So let's see here. So here it says that the breakthrough time is defined as the time at which the concentration at the exit of the bed C reaches a value of 0.05 C0, where C0 is the concentration of VOC in the feed. The breakthrough time for the bed is 2.1 hour. As we have shown in this figure, this breakthrough time here is 2.1 hour, and this is 0.05 C0. Um, the area under C by C0 curve between the initial and the breakthrough time is 0.1 hour. So here, basically, this is the area we are talking about. So this area under the curve, which of course is going to be the integral of time is equal to 0 to TB. Up to this point, this is my TB at this point. So this C by C times dt, that's equal to 0.1 hour. Why 1 hour? Because this is dimensionless. So this integral has the unit of time only, 0.1 hour. Okay. All right. So what which one of the following is the fraction of unused bed at breakthrough? As we say that even after breakthrough, there's a considerable amount of capacity of the adsorption capacity of the activated carbon bed is left. So it wants to know at breakthrough time, what is the total amount of unused amount of activated carbon, or the adsorption capacity remaining. That's what it wants to know. Okay, so why not? So the way we do it first is, what is the maximum absorption capacity of the bed at time t is equal to 0? That initially, this is WQV. So this is the 4 grams of carbon. So as we said, here we have in the bed we have 4 grams of carbon per square centimeter. As we said, we really don't know the cross-sectional area, but let's take a basis of 1 centimeter square. So we have 4 gram of carbon, and we had the maximum absorption capacity 0.4 gram of VOC would be absorbed at equilibrium per gram of carbon. Okay, so what's the total capacity is 1.6 gram VOC per square centimeter. That's the maximum. Okay, what is the next step? Total VOC absorbed up to the breakthrough time. For doing that, first we find the total VOC which has entered the column time till TB. That means till the breakthrough time. That would be equal to FTB. That means 0.2 grams of VOC per square centimeter hour. That is the amount of VOC entering. Remember, this is one. This is the VOC which is entering here. In fact, the entry could be other way also, something like this. Okay. Um, so this is the amount of VOC that is entering times 2.1 hour. So that's basically total amount that has entered is 0.42 gram of VOC per square centimeter. So if we see here up to this time, 0.42 up to this time, 0.42 gram of VOC per square centimeter has entered the column. What is the total VOC that exited from the top of the column to breakthrough? So remember, as we said, this is the bed here. This is, let's say, C0, and this is C. Okay, so this is the exit concentration. So to TB, what's the total amount of VOC that is exited? So that is the rate at which this is entering, which is 0.2 grams of VOC per square centimeter per hour, times the integral of this area, integral of the area under the curve here. So basically this one right here. So this is the area, C by C0 times dt. So, and this has to be multiplied by this concentration, that is 0.2 grams of VOC, which is entering per square centimeter hour, right? So what that is the total amount that has exited, that has gone out from the column. So this is, if you do the calculation, so that is 0.0 VOC that has gone out of the column. And this is the actual, so that much amount of VOC that has entered the column. These are all time till time TB. Okay. So what's the total VOC that is absorbed in the bed till breakthrough time? That means till TB. That is the total VOC which has entered minus the total VOC which has escaped. So that is this amount. So what is the unused bed capacity at breakthrough? That is the total capacity of the bed minus total VOC that has been absorbed till time TB. And if you do this count, that is 1.2 gram of VOC per square centimeter. Okay. So what is the fraction of unused bed capacity at breakthrough? Unused absorption capacity at time t is equal to TB divided by the maximum absorption capacity of the bed. So what is the unused bed capacity, which we calculated right here? So this should be equal to 1.2 divided by 1.6, that's 0.75. So all the details are, of course, given here. All the slides, copies of these slides are given in the website here. So as we can see, it's 0.75. So the fraction of the total absorption capacity that is still unused at time TB, which is still unused, is 75% is still left. It's still activated carbon, which is capable of absorbing the VOC. So how do we interpret this data? It says at breakthrough, that means when 0 by 0, 0.5, so this is according to the given definition, given the problem, 75% of the bed capacity remains unused. Okay. Of course, even after that, there'll be still absorption, but this concentration will now keep on increasing after breakthrough. So what could be the problem? It could be like poor mass transfer. It could be the channeling problem. It could be like poor gas distribution at the inlet. It could be insufficient bed depth, whatever. So that has to be seen by the engineer. Let's look at the practical process industry application. In chemical, pharmaceutical, electronic storage disks, components, paint, solvent handling plants, continuous VOC emissions are a big problems, and for that they are passed to fixed bed of activated carbon before the VOC-laden air is discharged to atmosphere. Typical VOCs are like acetone, toluene, xylene, ethanol, isopropyl alcohol, methyl ethyl ketone, benzene, etc. And there are a couple more. Okay, let's look at the typical VOC activated carbon adsorption system, which is used in the industry. I'll very quickly go through it. So this is where this air plus, let's say, VOC or the other gas plus VOC that is coming in. Of course, this is a blower, and that goes through this activated carbon bed here. And what happens? So this, as I said, this gets absorbed, and we have already discussed what is a breakthrough etc. And then the clean gas that really comes out from here, that is now sent to maybe a flare, or just discharged directly. Okay, but what happens after some time? Of course, this gets spent. That means all its absorption capacity has been totally utilized. And after that point, whatever the concentration comes in, the same concentration goes out. So we, of course, don't do that. Okay, so what we like to do, we would like to regenerate this one. So that's why there are two beds are used in tandem here. So let's say this is now working, and this is now being used for regeneration. So after this is regenerated, this will be working now, and this will be regenerated. That's the way it works. So how does the regeneration work? So here, let's say hot nitrogen, or sometimes hot air or steam, that is passed through this one, and it just goes up. And what happens is that here, from here, let's say the steam plus VOC, that the volatile organic carbon, comes out from here, because at high temperature, of course, the VOC that has been absorbed gets dissolved and driven out of the bed. So this absorbed VOC plus steam just comes out, and then of course there's a condenser here, and they're condensed, and we get the liquid VOC here in the liquid state. This is now probably sent to some kind of an incinerator, or if this can be reused, it can be reused, etc., etc. So this is a typical example of a VOC absorption system. Of course, there are a couple of different process instrumentations, and there are different monitors, and for signaling when absorption is done and when it should be sent for regeneration, the entire thing. Okay. So going back to the problem here, the answer is 0.75. D is the correct option.